Coralville Reservoir is a nice big puddle of water that's about 3 miles upstream from Iowa City. And no, that's not the one I wanted either. All right. That'll do. So this is a photograph of the Coralville Reservoir during the 2008 flood when, let's see, can you all see this picture? I'm not sure. The highlighting around the shared screen is not showing.
I can see like the whole desktop.
Oh, the whole desktop, really? Okay, that was supposed to be just that picture. Now you've got it. Okay, so this is the Coralville Dam during the flood of 2008. Let's see, that's a good color for this piece here is the outflow, the normal outflow, which can pass 10 to 20,000 cubic feet per second under emergency circumstances. And during the flood, that wasn't enough. And huge amounts of water, uncontrolled amounts of water, flowed over the spillway, and which had only overflowed twice in the history of the reservoir. Both times were major floods that caused huge amounts of damage in Iowa City. But the basic notion of this reservoir is that we have some amount of water flowing out of it, some amount of water flowing into it, and the storage capacity of the reservoir. It turns out that that the best way to think about this reservoir is, lost control there. Stop share, share screen, that screen. And we can talk about a number of different features of the reservoir. One of them is the volume of the reservoir as a function of the elevation. And the volume of the, as a function of depth. So, and what we get there is a cubic curve. So V is some function, V is some function, some constant of elevation cubed. And why is it a cube? Well, the reason is that your typical river valley is a V-shaped valley. And in Iowa, our V-shaped valleys are very shallow. And the slope of the riverbed, can be approximated as a straight line. So the water in the reservoir occupies an area that's bounded on one end by the dam, on the other end by that straight line of the river valley. And as the volume goes up, the area goes up. And it turns out for any solid bounded by a shape like that, the volume is proportional to the depth cubed. And it doesn't matter how broad it is, how pointy it is, the relationship remains the same. If a very broad, shallow valley with a gentle slope or a sharp, deep valley, it's always going to be a cube as an approximation. And approximations are good enough for most purposes. And so until you get up to the rounded hilltops, as long as you're in the bottom of the valley where the slopes are determined by various erosion rates and hilltops and roundedness of the hilltops doesn't matter, you get that kind of an approximation. But the next thing I'm worried about is the outflow as a function of time. So the flow as a function of time. I'm sorry, wrong issue. The flow is a function of elevation. Yeah, I've lost my pencil. The flow as a function of elevation is 0 until you reach the spillway elevation, and then the flow goes up, I believe, elevation to the 4th power. So at this point, flow is a function of, flow is equal to some constant, k prime, e to the 4th. And why e to the 4th? Well, it turns out that, of course, flow goes up as the area, as the unobstructed area goes up, flow goes up. But also, as the elevation goes up, we can think about, here's a cross section of the area of flow, and the velocity of flow, change color. The velocity of flow, if this is the water elevation, the velocity goes up. The velocity at the surface, the pressure at the surface is very small, but as you go down in depth, the velocity, the pressure increases linearly with depth, and the velocity increases quadratically with depth. And so you have to integrate that quadratic, and that means it gives you something approximately the flow being the 4th power of the elevation. This is stuff I vaguely remember. And so it doesn't matter. The details don't matter, but we get descriptions of clear all drawings. We can describe a whole bunch of different functions. We can say volume, annotate, volume as a function of elevation, and we can have flow is what? Flow is a function of the sluice gate setting, the deliberate setting. So this is the controlled setting, the controlled outflow, the sluice gate on the controlled one, plus the spillway flow, and the spillway flow Fs, and this is F capacity. The spillway flow is a function of elevation, and it's mostly 0 until the reservoir gets deep enough. And then you get the inflow as a function of time. that's given. And that has to do with rain and things like that. And the the volume as a function of time is this wasn't volume, that was something like that was oh yeah, that's volume. Volume is a function of elevation. The volume as a function of time is the integral of the inflow as a function of time. And the outflow, well, this gives us a system of differential equations, and we can use numerical simulation to derive the outflow under a given policy, and here's our policy. We want a policy which minimizes which minimizes loss. So we can run our simulations for different policies and determine our losses. This is a typical example of a continuous model.